So the last speaker for this part of the session is Thomas Morgan, and he's going to talk about the lunar sodium exosphere from ground-based observations.
Let me first of all make sure I can make this work. That goes forward. How do I go back? There. Where is the pointer?
Pointer is this. You hold it and point at the screen, and it's
Oh,
digital.
okay. I didn't see it at first. Thank you.
No problem.
This is the talk is about the lunar sodium exosphere, which is a subject that has been around for the moon for over 30 years. It's hard to imagine that. I was much younger when I first encountered it. My co-eyes here are Drew Potter and Rosemary Killen and Roy Tucker and Jamil Johnson, and they have a lot to do with the fact that we have anything to show. The Dream 2 symbol is there because of Rosemary. I can't see my own talk very well. Can you hear me very well in the back? Okay. The lunar sodium exosphere has been observed for about 3 decades, and it's curious that nobody has nailed down the source process. There are at least three, but there are three that I like. Photon-stimulated desorption, impact vaporization, and sputtering. And you would think, since we relatively know the abundance and we know the fluxes of these things, we would long since have worked all this out, and it would be part of the trivia of the solar system. That hasn't quite happened, and it's very interesting because these processes work all over the solar system. So all three contribute. We're not sure which one is dominant. And this was a project to try to build up a database to determine if we could identify which one was the important one. The goal, that was the goal of the project. Our method is to try to measure the distribution of sodium above the surface from just above the surface, a few hundred kilometers above the surface, out to about 1 lunar radius. We picked that because we think that region is important, and also because people have worked in the other regions. For example, the far distribution of sodium has been observed many years ago. It's quite interesting, but it really isn't going to allow us to address, we think, effectively, the issue of sources. Well, I just said what my next bullet is. It fills a gap in the ground-based observations. LADEE observed sodium, but it only covered a few lunations, and 2 of these processes, one of them in particular, impact vaporization, you just can't do that on 100 days. You've got to have a long period of time because you're dealing with what is to some extent a stochastic process. You can't control it. I just showed you that this is down here. This is down here just to remind you the early observations often got it wrong because we just had a small amount of data. This was a discovery observation, and this is about 50 kilometers, and of course we got the scale height wrong. You have to have a lot of spatial coverage to really understand what's going on. I'll mention that there are other ways to study this, and there's a poster by Oliverson et al. Is it still up? Is Ron here?
Yes.
It's still up, which shows you another technique for going after the sodium exosphere. Lest I get terribly behind time, let's keep going. Where? We're going to set up something so we can get frequent observations, and we have to have a telescope. And so the where we put it is the Weiner Observatory in Sonoita, Arizona. There are a number of other groups who want to use small telescopes for continuous or near continuous observation at night, and this particular facility is designed for that. You notice there's a rollback roof, and there inside that area are 4 telescopes, one of which is ours, and all of them are designed to get many observations done robotically or remotely. And so this facility is designed for that, so that's where we've located it. Whoops, did I go backward? No, I didn't. Why do you use a coronagraph? Most of you don't come out of astronomy, so you don't want to know what a coronagraph is. But your observational problem is that you have an extremely faint largely extended mission right next to the second brightest object in the sky. That's our problem. We'll see a picture in a few minutes, and you'll see it. Most astronomical telescopes are not optimized to solve the scattered light problem. A coronagraph, without going into great detail, is simply an optical system designed to minimize the scattered light, and it is simply a very, very good camera. That's the zeroth order for a coronagraph. We take images on and off the emission line with a tunable narrowband filter and with an occulting disc alternately in and out of the focal plane, the first focal plane. So our field of view is about 1.5 degrees. I'm going to walk away from the, I can't, I have to point. This is the width of our filter, and about 1.5 degrees angstroms. This is on top of a spectrum right off the lunar limb. So you see sodium and you see scattered light, because even if we get the scattered light out of the telescope, there's scattered light in the sky. I think everybody's familiar, everyone here has sometime in their life has seen the sodium doublet in a physics lab or in a lamp outside at night. And this is one of those two lines, one of the two sodium D lines. And that's what we're observing. This is our, Roy Tucker is one of our co-eyes, and this shows him with a partially assembled coronagraph. I won't go into a lot of detail about this, but this is simply the main telescope, a finder. The occulting discs are kept here. There are 6 of them because, of course, the moon is not always a constant size. As you go through the year, the apparent diameter of the moon changes, so you can't just use one occulting disc. It's re-imaged. There's a sodium filter. Whoops. If I could just get these buttons right, I'd be fine. And finally, a camera. This is another picture with a lot of the stuff that was left out there on. And this is what we use to take the data. This is done remotely. We have 2 remote stations. One is at Goddard Space Flight Center. And this shows you, dadgummit. This shows you, on the one hand, the guide scope. That looks just like the moon. And this here is the automatic guider. And here is the last image we took with the science camera. And all these applications that appear on this screen are actually commercially available. This remarkably good tracking system is something we were able to get and make work. We have a colleague, Drew Potter, who lives in Prescott, Arizona, who has his very own setup, and so can support us on observations. And it's really great to have somebody in the telescope's time zone, as we're not. This is a simple picture, coronagraph left, and so there you see the occulting disk, and you see the corona about the exosphere of the moon. And so over here we have a picture which shows a superposition of the moon, a half-second exposure of the moon placed on the 600-second exposure of the lunar sodium exosphere. I keep wanting to say corona, but it's an exosphere, it's not a corona. This is another way to look at it. This is a polar transform. So what this means is that you can go across here. It's like cutting from the center of the moon and going out. So you can use this to make scans across this way. All right. The results we have are the data from the spring of 2017. Excuse me, and they are surface number density, scale height, and column abundance as a function of phase and latitude. One thing I forgot to mention is it's still looking from the ground. I think I said this, but I put it in the slides, but I didn't say it. But it takes exactly one cirrus cloud to knock us out of business. So there are many nights when you get something and other nights when you don't. This shows the waning phases of the moon. This is column abundance and surface density. And the thing that really stands out here, if you look at all the spaghetti, is that there is an asymmetry in this. Right about like that. And that surprised us. In other words, there's more sodium typically in the south and less in the north. And that shows up both in the column abundance. Remember, column abundance is just you look right along the line of sight and add up all the sodium. And number density is a derived number because you're putting in a scale height. This surprised us, but it turns out if you look at where you're looking over that limb of the moon, there's some reason for this. The Chandrayaan-1 had a CIXS instrument on it, and it derives sodium abundances, regional sodium abundances, and that's actually an area of increased 2 to 3% sodium abundance, which makes perfect sense because you're supposed to mine the sodium from the surface. So it's comforting, actually, that that's the case. This is waxing phases. It doesn't look the same at all. If I do something daring and try to repeat the last slide, there. To 0th order, they're very different, aren't they? We don't fully understand that, but that's the way it is. I want to note that we've seen some interesting phenomena here. For example, I have to check because the color coding drives me crazy. We have two sets of data that look rather anomalous. They're 117 and 118, and they occurred when there was a report of an impact flash from the group, I think, down at Marshall that does it. And that to us is interesting, and it means if we look at enough of these, if we keep observing and we start seeing things like that with anomalies, it begins to make a case for one of the processes, namely impact vaporization. Now I've got to get back on topic. The other thing we wanted to show here, this is a real struggle for the viewer. Those little asterisk-like things are a cosine fit to the data, or an attempt at it. And the cosine fit is because that's what you would expect to 0th order if you had photon-stimulated desorption, without going into vast detail. And it really doesn't fit very well. Okay? All right, since I've got 2 minutes, I'll give you our conclusions that the lunar sodium exosphere has latitudinal asymmetries, and as I said before, I think that makes sense. It's supposed to. Surface number density for waning phases show a persistent southern enhancement. I didn't catch this, but it's true. Surface number density for waxing phases peaks at mid-latitude. The latitudinal variation is always flatter than a cosine, which again is a hint that photon-stimulated desorption is probably not the major process. I didn't talk about scale heights very much. I should have. What a scale height really tells you is it's hot. The sodium exosphere of the moon is hot. And so it's about 45 degrees Kelvin, which also hints at an energetic process. And our future work, this is all the data that we haven't reduced. And we have a natural cycle because the moon sonde comes into Tucson right about now. And those are the 3 months that we try to catch up with the rest of the year. So if you're lucky, next year we will have most of this done. And that's it. Thank you very much.
So, questions?
Sir?
Hey, nice talk. Let me ask you a quick question. Did you have enough of a data set, and particularly if you start doing all of this, to start correlating observations sort of on a night-by-night basis with solar activity, solar wind activity, and you could actually start doing long, kind of multi-month correlations? Have you thought about that? That would be kind of...
Well, we have thought about that. That was many years ago. That's why we started this process. But yes, we've got to work our way through the data. But that's exactly right. And our real struggle is that even if you have a dedicated telescope, you can't control the weather. And so because you can't do that, you're going to have to get a lot of data. And that is the advantage of having your own little telescope. Nobody starts arguing with you about they want to look at something else. We have a telescope that can only look at one thing.
Ronald Leverson, NASA Goddard. Taking that very approach, we have 6 years worth of sodium data taken from the solar McMath. Different technique, we're doing high resolution spectroscopy on sodium from 2011 to 2017, and then 2014 to 2017 in potassium. And if you use a solar telescope at night, you can pretty much get as much as you wanted. Unfortunately, they closed it last December. But that is one of our objectives there, to look at the solar cycle, also look at, do we coincidentally see any meteor streams? And then fortunately, we do have an overlap with some of Tom and Rosemary's data there to do a comparison and help with our calibration.
Are there any other questions? Oh, I'm sorry, I'm doing...
And after this question, we'll move to the discussion. So I'll have the other three speakers come back up.
Okay.
Do you have any idea as to what that energetic process is that you mentioned that heats up the sodium?
From what everything that I understand, the most effective process for getting energetic sodium is impact vaporization. It just produces a hot vapor, and there's a lot of evidence. You can do this comparatively. The moon is a weak sodium exosphere. There are other places in the solar system where there are much brighter ones, one of which is Mercury. And so we can do the compare and contrast between the moon and Mercury. And I think that impact vaporization has, not only for sodium, but for other elements, become an increasingly important process there. The process produces other elements, and in the case of Mercury, they're bright enough to see. The moon has a very small exosphere. For example, it would be very hard to look. There's undoubtedly a weak iron exosphere. I don't think Laddie saw it. I don't remember. But it's really hard to see. I mean, the sodium is an accident of the fact that we live around a G2 dwarf, and sodium has some very strong resonance lines, right at 5,800 angstroms. And if you look for other species, but if I integrate over everything we know about exospheres, about these surface-bounded exospheres is a not very exciting term. They're exospheres with a rock at the bottom. I think that impact vaporization is the hot process in the sense of producing high energy, a big scale height. Photon-stimulated desorption doesn't do it, and I don't really think that sputtering does that much. But it's a good question, but I really think it's a question where you think, you don't answer it with the moon, you think bigger. Sir?
Okay, let's thank our speaker again.
Nope.
Oh,
Well,
save it for the discussion.
Yeah.
And you can, yeah. Okay, let's thank our speaker again. And